Okay, so we've looked at how to take a system and write it in its augmented as an augmented matrix. We've looked at some examples of row operations. How do we manipulate rows? We can do swapping. We can multiply a row by any sort of constant that we want. We could add rows together. So let's talk about how to pull these new tools together to solve a system. The first method that we're going to look at is we're going to talk about how to solve a system using Gaussian elimination. The process that we use to solve a linear system using matrix row operations is called Gaussian elimination, after the German mathematician Karl Gauss, who lived in the 17 and 1800s. The goal when solving Gaussian elimination is to get a matrix with ones down the main diagonal and zeros below it. So here is the example of the goal that we're trying to get to. We want ones down the main diagonal. So when you think about this diagonal, you want everything in the diagonal to be 1. And we want zeros below the diagonal. So everything below the diagonal needs to be 0. Now when we get here, we're going to be amending some values. A, B, and C are just going to be the results of the coefficients. And then D, E, and F are just going to be the resulting constants. This matrix, this form of a matrix, is called row echelon form. And here are the steps. Now you can go back and read these steps, so I'm not going to go over them completely, but the first goal, it's going to highlight this, the first goal is to get a 1 in the upper left-hand corner. So we want this to be a 1. That's the first goal. Then the second goal is to make everything below that 0. And we're going to use row operations to get there. Then the third goal, again, we want to make a 1. We want to make a 1 in the second row, second element. And then we're going to use that 1 to our advantage to get a 0 below it. And then our final step is to get a 1 in the third row, third element of the third row. Once we get it to this form, the nice thing is we can start solving. We're going to immediately be able to start saying things like this. Well, since this 1 represents the coefficient of our z's, we can start saying that 1z is equal to, let's call this D, E, F. 1z is equal to f, or just z is equal to f. And once we get what z is, we can use back substitution to find y, then x. We can use back substitution to find the remaining variables. So let's go through and do some problems. What we're going to do is we're going to break this approach down. We're going to look at a 2x2 system first, how to do this with a 2x2 system, and then we'll elevate the problem to a 3x3 system. So here we go. First thing that we want to do is we want to get this system into its augmented matrix. Again, I like to look at them as columns. So when I look at my x's, I got -4, then 1. Those are my coefficients. Then my y's, I got 3, 2, equals 25, negative 9. All right, so let's keep in mind what are our goals. What we want is we want this to be 1. Want to be 1. Now, I could go through and divide everything by negative 4, because negative 4 divided by negative 4 would be 1. But that would introduce fractions. And if I can avoid introducing fractions, I'm going to avoid introducing fractions. I see a 1 right here. So what if we were just to swap these two rows? Then that would get what we want. We want this first element in row 1 to be a 1. Well, what if we just swap the rows? So let's take row 1 and swap it with row 2. That's going to give us 1, 2 equals negative 9. Negative 4, 3 equals 25. Now we've achieved what we want. Remember, the first goal is to get this first element in row 1 to be a 1. Now what do we want to do? Well, going back to that goal sheet on the previous page, we want this element to be 0. We want to be, I'm not going to do that shorthand. Want to be 0. We're going to use the fact that we have a 1 right here to our advantage. So here's the row operation that immediately comes to mind. Let's take 4 times row 1 and add it to row 2. Because 4 times row 1, 4 times 1 would be a positive 4. Combine that to a negative 4 would give me 0, exactly what we want to happen. Notice again the way I notate this, since this row operation is in line with row 2, row 1 does not change. Now, maybe you want to do some work. So let's do the work. So 4 times row 1 would be 4, 8, and then negative 36. Combined with row 2, negative 4, 3, 25. We get 0, 11, and then a negative 11. Zero, 11, negative 11. Close off my bracket. Now, you can see that we've gotten to the end of our paper, so to speak. I'm not going to try to squeeze in an operation over here. For good communication purposes, I'm just going to rewrite this last matrix down here. Another way you could have done this is you could have maybe written your row operation here and then write the result down below. In fact, I'm going to use technology to my advantage here. I'm just going to take that and move it down here. Isn't technology amazing? All right, there we go. All right. Now, the next thing that we want to happen is we want this second element in row 2 to be a 1. Now, immediately I see this negative 11 over here. 1 and negative 11, they're multiples of each other, which is good for us because we can do something as simple as 1/11 times row 2 to get what we want. So again, let me write down what we want. We want this to be a 1. So here's how we do this. We multiply it by a 1/11 or divide by 11. 1, 2, -9, 0, 1, -1, and we're done. This is now in what we call row echelon form. Now here's where we start solving. The first thing that we can imply here is this, that y is equal to a -1. We have a coefficient of 1. There is no x here. So we have 1y is equal to -1. That means y is equal to -1. And then I'm going to use back substitution to start solving for x. So the next thing I'm going to do is I'm going to take row 1. Row 1 implies that we have x plus 2y equals a -9. We know that y is equal to -1, so I'm going to plug in -1 for my y, and we get the following. X minus 2 is equal to -9. Then we'll add 2 to both sides. We get x is equal to a -7. And there we go. We can now declare that we have a solution. Make sure your solution is in terms of x and then y, -7, 1. Now, before I box that in, I'm going to check. You either check physically by doing out the work, or you check mentally. -7 times a -4 is a sorry, -7. I miswrote this. I was getting confused. I had to pause the video. I missed something, didn't I? What was y? It's a -1. That fixes my confusion here. So -7 times a -4 is a positive 28. -1 times 3 is a -3. A positive 28 combined with a -23, but combined with a -3 is 25. Check. And then -7 plus 2 times a -1, so -7 plus a -2 is indeed a -9. Everything works out. So we're good. So let's apply this process of reducing a matrix to row echelon form with a 3x3 system. Here we go. First things first, we want to get this into an augmented matrix. So looking at this in terms of columns of coefficients, we have 2, 1, 1, 1, -1, 2, 2, 2, -1 equals 18, 9, 6. And the first thing that we want is we want this to be 1. We could divide by 2 again. Unfortunately, that would introduce a fraction right here. So instead, I'm just going to do a simple row swap. I'm just going to take row 1 and swap it with row 2. I'm going to do a simple row swap. So we now have the matrix 1, 2, 1, negative 1, 1, 2, 2, 2, 1, 9, 18, 6. All right, already I can tell that I don't have enough room over here to put the next matrix, but I can at least write down the row operations. What we want next is we want these two elements to be 0. And we're going to use this 1 that we have right up here to our advantage. Now, perhaps in these operations, there's more than one way to do things. So you might come up with something and your friend, your neighbor might come up with a different operation. Again, as long as we're all getting to the same result and our work leads us there, and we're all good. So here's what I did. I'm going to take negative 2 times row 1 and add it to row 2. So that's going to give me a negative 2 here, combined with a positive 2 is 0. Then I'm going to take negative 1 times row 1 and add it to row 3. And that's going to give me the augmented matrix. I'm going to write this out now in rows instead. So row 1 does not change. 1, negative 1, 2, 9. And I'm also going to do this work mentally. So here we go. Negative 2 times 1 is a negative 2 combined with a positive 2 is 0. Negative 2 times a negative 1 is a positive 2 combined with a positive 1 is 3. Negative 2 times a positive 2 is a negative 4 combined with a positive 2 is a negative 2. Negative 2 times 9 is a negative 18 combined with a positive 18 is 0. That takes care of row 2. Now row 3. Negative 1 times 1 is negative 1 combined with 1 is 0. Negative 1 times a negative 1 is a positive 1 combined with a positive 2 is 3. Negative 1 times a 2 is a negative 2 combined with a this is where you got to be so careful. What am I missing? We have 1, 2, negative 1, 6. 1, 2, negative 1, 6. You got to be so careful with your signs. You got to be so careful. So back to this operation, negative 1 times 2 is a negative 2, combined with the negative 1 is a negative 3. And then negative 1 times 9 is a negative 9, combined with a 6 is a negative 3. All right, so the next thing that we want in our goal is we want this element to be 1. Dividing by 3 does not sound like a good idea because I introduced a fraction here. So again, I'm going to do a simple row swap. Now, why am I going to do a row swap? Well, I see down here in row 3 that everything is divisible by 3. So again, this is where you can do your neighbor might do one thing and you might do something else. We could divide this row by 3 right now and then do our swap. Or we can do our swap now and then divide. I'm going to do the swap now. I'm going to take row 2 and swap it with row 3. So row 1 does not change. Row 2 is now 0, 3, negative 3, negative 3. Row 3 is now 0, 3, negative 2, 0. I still want this to be 1, and the way we're going to do that is we're just going to take 1/3 of row 2. So looking at the rows, 1, negative 1, 2, 9. Divide row 2 by 3, you get 0, 1, negative 1, negative 1. And row 3 stays the same, 0, 3, negative 2, 0. Okay, now let's talk about what we want next. What we want next is we want this element to be 0. We want that element to be 0. We're going to use row 2 to our advantage. The reason that we don't want to use row 1 is because if we add row 1 and row 3 together, this 0 gets undone. Remember, that was part of our goal up here. We wanted this to be 0. Well, if you add row 1 and row 3 together, that 0 gets undone. But adding 0 and 0 together does not undo the work that we've already done. So I'm going to take negative 3 times row 2 and add it to row 3. That's going to give us the new matrix. Row 1 and row 2 do not change. We still have 1, negative 1, 2, 9, 0, 1, negative 1, negative 1. Now let's go through and do this mentally. So notice that 3 times 0 is still 0, plus 0, we're still going to get 0. Negative 3 times 1 is a negative 3, combined with a positive 3 is 0. Negative 3 times a negative 1 is a positive 3, combined with a negative 2 is 1. And then negative 3 times a negative 1 is a positive 3, combined with 0 is 3. Now, the next goal that we want to have happen, according to our set of procedures on the previous page, is we want this to be 1. Well, it's already been taken care of for us. It's already been done. Now, if that was not 1, we would need to multiply or divide by some number so that this becomes a 1. We would need to multiply this entire row by something so that we get 1 right there. But since it's 1 already, this is where we can start making some implications. The first implication that we can say is this, that z is equal to 3. Then we get to start working backwards. We'll go up to row 2. Row 2 says that y minus z is equal to negative 1. We're going to use the fact that z is 3, so this means that we have y minus 3 is equal to negative 1. We would then add 3 to both sides, and we get that y is equal to 2. So what we did was we did a substitution. We let that z become a 3. Now we know what y and z are. Now we can work backwards to solve for x. This row implies that x minus y plus 2z is equal to 9. Using the fact that z is equal to 3 and y is equal to 2, this becomes x minus 2 plus 2 times 3 is equal to 9. So we get x, 2 times 3 is a 6, combined with a negative 2, so that's going to be x plus 4 is equal to 9. Subtract both sides by 4, and you get x is equal to 5. So we have the solution (5, 2, 3). Now, it's about to say before you box it in, so let's undo that boxing in. We want to check. Checking is so important in this process. So here we go. We're going to look back up at the original system, and we're just going to plug things in. So here we go. 5 times 2 is 10. So let's look at equation 1. 5 times 2 is 10. And then we have plus 2. And then 2 times 3 is going to be 6. Does this equal 18? Well, 10 plus 2 is 12, plus 6, that's 18, is equal to 18. Check. Then we'll go and check it with equation 2. So we have 5 minus 2, and then 2 times 3 is going to be 6. Does that equal 9? Well, 5 minus 2 is 3, and 3 plus 6 is equal to 9. Check. Then when we go and look at equation 3, we have x, 1x, that's going to be 5, plus 2y, so 2 times 2 is 4. 5 plus 4 minus 3, is that equal to 6? Well, 5 plus 4 is 9, and 9 minus 3 is 6. Check. We've taken our solution, and we've checked it with all 3 of the original equations. They all work out, so now we can confirm that this is indeed our solution. And this is Gaussian elimination. In the next video, we're going to talk about the call it the next iteration of Gaussian elimination, Gauss-Jordan elimination.